Today we're going to finish off our two-dimensional vector analysis and move forward to applications of two-dimensional vector analysis. Last question that we're going to do here of the type that we've done, question that I gave you yesterday when we were leaving. We got, how many vectors was it? 1, 2, 3, 4, 5, 6 different vectors, 3 of them at funny angles that we've got to get rid of. So that's what we're going to do first, is get rid of all 3 of these funny angles. Let's label them here. Because there's so many of them, let's start number them here, okay? We're going to say this is vector number 1. We're going to say this is vector number 2, number 3. We're going to make this one number 4. This one's going to be number 5. And this one's going to be number, let's change the color around a little bit there. Let's make this one number 6. We want to find the x and y components of vector 1, 4, and 6 so that we can get rid of that 100 meters, that 50 meters, and that 20 meters. All right, let's deal with the first one first. Vector number 1. Let's label it just because we're going to have a lot going on here. We want to be able to sift through what we're doing and make sure that we can keep everything organized here. Vector number 1, we got 100 meters down this way. 30 degrees inside our triangle. This is our x, this is our y. Which side of the triangle, Sonia, which side of the triangle is the x component here? Is it opposite or adjacent? Good, so we're going to use the cosine function to find it. Cosine 30 degrees is equal to x over 100. X is equal to 86.6. And we're going to use the sine function to find the y component, which is opposite. Y ends up being equal to 50 in this case, right? Let's square this off. And now let's go over here and replace that vector 1 with the 86.6 and 50 meters, both negative values because they're both down and to the left. So this was 50 meters down and 86.6 meters to the left. The next one we got to deal with is vector 4. Vector 4 is 30 degrees. What would that be? 30 degrees what of what? Not that we really need to know that for this question, but it's good practice. 30 degrees, it's measured from the west axis, and it's going north from the west axis, so it's going to be 30 degrees north of west. Let's deal with that 30 degrees north of west. This is our x, this is our y, this is 50. Olivia, which side of the triangle is the x-axis here? Is that opposite, adjacent, or hypotenuse? It's adjacent again, so we're going to say cosine 30 degrees is equal to adjacent over hypotenuse. Most times, x goes with cosine. I'd say probably 3/4 of the time, x goes with cosine. So if you got to guess cos for x, sine for y. But that's not necessarily going to be the case. There's not a 100% chance of guessing that, right? So you want to make sure that if you can distinguish between when to use cos and when to use sine. X ends up being equal to, what is it, 43.3? And we're going to say sine 30 degrees is equal to opposite over hypotenuse. And y ends up being equal to 25. All right, let's square that one off now. And let's redraw that one. Let's get rid of vector 4 and replace it with, we had 25 up and 43.3 to the left. Now, I could have drawn the 43 first and then the 25. It doesn't really matter, but I just thought it was a little bit more tidy to do it this way, because if I had drawn the 43 first, well, it would have kind of went back upon the other vector. Just would have been a little bit messier. It would have been correct, but just not quite as neat. So that's the way I chose to draw it. Doesn't really matter, though. Okay, now we got vector number 6. We're going to go off to the side and draw that one. Vector 6 is at 60 degrees. I'll just do that over here. 60 degrees. This is X, this is Y, and this is 20. For this one, Tori, for this one, is X the opposite side of the adjacent side? It's the adjacent side again, good. So we're going to say cosine 60 degrees is equal to adjacent over hypotenuse. X ends up being equal to 10, I think. Here, so. Yeah, that's right, yep. Sine 60 degrees is equal to opposite over hypotenuse, which equals 17.32. Let's square that off. And now let's deal with that vector. Get rid of that. We had 10 to the right, and we had 17.32 down. Good. We've just turned this question into, well, basically the question that you had on your quiz, right? Except with more vectors. Now we've got everything either on the x-axis or the y-axis, and that's good news for us because we can deal with that pretty easily in the grand scheme of things. Okay, we got x, we got y. Now let's look at vector 1. The x component of vector 1 is going to be what? Ben, what's the x component of vector 1 going to be? Vector 1 is the green one, by the way. David, what's the x component of vector 1? Good, 86.6. Good, negative 86.6. And what's the y component of vector 1? What's the y component, Miles, of vector 1? It's going to be negative 50. Good. You guys are not only getting the numbers, you're getting the signs as well. That's good. Okay, vector 2. The x component of vector 2. William, what's the x component of vector 2? Vector 2. The x component. No. 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 Good. The x component of vector 2 is 0. Only took 2 guesses. Good. What's the y component of vector 2? Excellent, William. On the first try, negative 50 for the y component of vector 2. What about the x component of vector 3? What about the x component of vector 3? Who should I call on this time? Robbie? It's going to be 300. What's the y component? 0. Good. All right, we're getting there. Vector 4, the x component was Everett? It's the blue one. Good. Negative 43.3 because it's to the left. And the y component, Everett, is? Good. Vector 5, which is this black one right here. The x component is 0, and the y component is? Good. Oh, we're just about there. Now vector 6, the last one, the purple one, the x component is? The x component is, let's see, Taylor. It is 10, good. And the y component is? Close, yeah, negative 17.32. So we got to add these up now. You get 180.1. We add the other ones up. And we get negative 100, negative 200, negative 175, negative 192.32. Now we got to combine them. Now the hard part's done. Like really, all these off to the side things are the hard part. We got 180.1 to the right. We have 192.32 down. And the resultant vector here is going to go from start to finish. This is theta, always drawn at the start of my vector diagram, and this is going to be r. Theta is going to be found by taking the inverse tan function of opposite over adjacent. This side of the room, okay, Nick's side of the room and over is going to find the first one, R. Everybody is on their calculators. And this side of the room, Fraser's side and over, everybody is going to find the value of theta. 263.1, 0.5, 0.15 or 0.5? Okay, so there we go. 263.48 meters. How many digits are we going to round that to? Let's go back to our original data. And it looks like we have 2 digits in our original data. So we're going to have to round this to 2 digits, which equals 2.6 times 10 to the 2 meters. 2.6 times 10 to the 2 meters. What's, excuse me, what did theta work out to be here? 47 degrees to 2 digits as well, 47 degrees. Now, how do we express that? 47 degrees what of what? North of east, south of east, east of south. Yep. This one would be south of east. And how do you know? Because we're measuring the angle from the east axis. You could argue that you're measuring it from down here as well, but we're not going to call that an axis. This is the only axis we're measuring it from, and that's the east axis. So we're measuring it from the east, or of the east. It's south from the east, or south of the east. So there's our answer. 2.6 times 10 to the 2 meters at 47 degrees south of east. This is what you got to be able to do on your quiz tomorrow, just less of it. We're going to spend some time today applying our new knowledge of vector diagrams and vector analysis to solve what we call navigation problems or relative motion problems in 2 dimensions. We can already do relative motion problems in 1 dimension, but we're soon going to be able to do them in 2 dimensions. Let me give you an example of a relative motion problem in 1 dimension. Let's say that an airplane is traveling at 800 kilometers per hour to the east, and a baseball is, for whatever reason, thrown inside the airplane at 100 kilometers per hour. What's the relative velocity of the baseball? Or another way we could say that is, what's the velocity of the baseball relative to the ground? By the way, I wouldn't recommend doing this. If you're ever in an airplane with you happen to have a baseball in your hand, I probably wouldn't throw it at 100 kilometers per hour inside the airplane. Okay, not only are you risking damage and your own safety, but you might get arrested if that happens. Who's got an answer for this question? What is the relative velocity of the baseball? How fast is the baseball moving relative to the ground? I'll tell you what, it's a little bit of a trick question because there's 2 answers here. Depending upon something. I want you to tell me what it depends upon. Yeah, which way do you throw it? If the airplane is moving to the east and you throw the baseball at 100 to the east, then the velocity of the baseball relative to the ground will be 900 kilometers per hour to the east. If you throw it to the west, then the velocity of the baseball would be 700 kilometers per hour to the ground, right? How do we find relative velocity? We add vectors together. Now you see maybe where we're going with this, right? We've just spent the last several days adding vectors together in 2 dimensions. When we want to find a relative velocity, we add vectors together. A week ago, we knew how to add these vectors together. 800 plus 100 is 900, or 800 plus negative 100 is 700. Now we know how to add vectors together if we're in 2 dimensions. So in other words, the airplane's traveling to the east, you throw a baseball to the south. Now we know how to find the relative velocity of the baseball relative to the ground when we're in 2 dimensions, not just in 1 dimension like we could have done a week ago. So to find the relative velocity in this example that I just gave you, we added the vectors together. Again, that's what we're going to do. That's what we're going to do again in 2 dimensions. But to do it in 2 dimensions, to add vectors together in 2 dimensions, we've got to draw a vector diagram, right? The goal, remember, is always to get a right-angled triangle vector diagram. So these questions aren't going to be, oh, okay, a guy walks 10 meters to the north and then 5 meters to the east. What's his velocity? What's his displacement? These questions are going to be, oh, wait, you got an airplane that's flying to the north at 100 meters per second. Oh, but there's a wind to the west. What's the velocity of the airplane relative to the ground going to be? In other words, where does the airplane actually end up going as a result of both of those things? Sounds different, but it's really the same thing as what we've been doing. We're adding vectors together, except this time we're usually adding velocity instead of displacement vectors together. Now, the strategy that I like to follow when we're solving these problems is to break our vectors down into kind of two categories. One category is solid line vectors, and one category is dotted line vectors. And I'll distinguish between those in just a moment. But the bottom line is, because you're not normally, on quiz day or test day, going to have colors, multiple colors available to you like I do when I'm drawing on the smartboard, we're going to distinguish between the two types as solid and dotted lines. When exactly do we have what I call solid line vectors and what I call dotted line vectors? Well, here's the deal. A solid line vector is going to be what contributes to the motion. Okay, what contributes to the motion? What contributes to where we actually go? They're contributing vectors. For instance, if you're going across a river in a little boat, the river current contributes to where you go. You don't go in the direction of the river current, but it contributes to where you go. So we'd call that a solid line vector. If you're flying in an airplane and there's this really strong wind that's blowing to the west, you don't go in the direction of the wind, but it contributes to where you go. So that would be a solid line vector. If you're flying in an airplane and the pilot of the airplane is aiming straight north, you don't necessarily go straight north. The wind might blow you off course, but you're aiming straight north. Okay, that's going to be a solid line vector because it contributes to where you go. You're driving in a car. You ever notice this how many people have your driver's license? Okay, you're driving in a car, you get a Chinook wind blowing from the west towards the east. It's really, really windy. You're driving in towards Calgary, and you've got your steering wheel turned like this to go straight on the highway. You ever notice that? Like you got to really, really turn to the west to compensate for that wind. In other words, you're essentially aiming like up there somewhere, right? Kind of northwest somewhere. That's not where you go. Okay, that's where you're aiming. That's a solid line vector because it's not where you're going, it's contributing to where you're going. You're going north in that case, but where you're aiming is helping you, contributing to you going north. Those are all solid line vectors versus dotted line vectors, which are, that's where you go. Okay, that's where you really go. We'll call that the resultant. Or the results of the contributing vectors, the results of all of those solid line vectors, the result of the wind, the result of the river current, the result of you aiming in a particular direction with your steering wheel. Some examples of solid line vectors that contribute to where you actually go. When somebody aims or heads in a particular direction. The wind speed or the river current. The air speed, which, by the way, is the speed in still air. If you fly in an airplane, I don't think WestJet does this actually, but Air Canada does this. They fly all kinds of different types of airplanes. And if you look at the magazine in the seat back in front of you, in the back of that magazine, they used to do this at least, they list all the different types of airplanes that they fly. And then they have some information about those airplanes that they fly, the capacity, the wingspan, the airspeed. The airspeed of the airplane, 800, 900 kilometers per hour, that's the speed if there is no wind. That's the speed in still air. That's not necessarily how fast that airplane goes. If there's a headwind or a tailwind, maybe the airplane goes slower or faster than the actual airspeed, right? But how fast the airplane can travel without a wind Okay, the airspeed of the airplane contributes to where we go, contributes to where the airplane goes. So that's going to be a solid line vector as well. Now, what about dotted line vectors? What about resultant vectors? In other words, where we actually go. Okay, there's a wind blowing to the east. The pilot of the airplane is aiming to the north. Where do we actually go? Where does the airplane actually end up landing? That would be a dotted line vector because it's the result of the contributing vectors. Remember, the dotted lines are the result of the solid lines. Maybe we don't end up in a particular place, but we want to. Where we want to go would also be considered to be a dotted line vector, a result. Whenever we want to go somewhere, we'll just pretend we get there. And we'll make it a result of solid line vectors. Another resultant vector, dotted line vector, is the ground velocity, or the velocity relative to the ground. Okay, that question that I gave you involving the baseball and the airplane. You solved for the velocity relative to the ground. Had we drawn that out, we would have drawn that out as a dotted line vector because it's the result of how fast the airplane was aiming, 800 kilometers per hour, or the airspeed of the airplane, 800 kilometers per hour, and this other contributing factor where we're throwing the ball. So you can remember these are important, but the most important thing is to remember this. Solid line vectors contribute to my result. Solid line vectors contribute to my result, my dotted line vectors. Dotted line vectors are the result of contributing factors. Let's do an example. It says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. I'm not sure why the pilot of a plane would want to go to Edmonton. I'm not sure why anybody would want to go to Edmonton, but the pilot of this plane is heading directly north to Edmonton. That's where they're trying to go. But there's a velocity or the wind of 50 kilometers per hour to the east. That's a strong wind, 50 kilometers per hour to the east. Where does the plane actually end up going? We're aiming to the north, but there's a wind to the east. That wind is going to take the airplane off course. How much off course? Where's it going to actually end up going? So the first thing we got to do is draw this out. We have the pilot of a plane heading directly north at 200 kilometers per hour. Tell me, is that a solid line vector or a dotted line vector? In other words, does where this pilot heads, does that contribute to where the plane really goes? Or is that where the plane really goes? If it contributes, we're going to make it solid. If it is where the plane goes, we're going to make it dotted line. What is it, David? It's solid line, yeah. So we're aiming to the north. We're heading to the north, but that's not necessarily where we actually end up going. We're going to make this 200 kilometers per hour a solid line vector. First time we've drawn a vector diagram involving velocity, but there's no reason why we can't do that. Velocity is a vector just like displacement is. We get a 50 kilometer per hour wind blowing to the east. Is that a solid or a dotted line vector? Does the wind contribute to where we go? Or does the wind is that actually where we end up going? Rosie? It contributes. So it's a solid line vector as well then, right? We have two solid line vectors, 200 and we got 50. What's the rule for adding these two vectors together again? How do we draw that diagram? They've got to be drawn blank to blank. No, that's the resultant that's drawn start to finish. When we're adding vectors together, they have to be drawn front to back. Here's the front of a vector. Here's the front. You can't draw it like this because that's front to front. We could draw it like this. That's drawn front to back, right? The other option is that we could draw it like this. Okay, that's drawn front to back. Either one of those is okay. Now remember, just like in the problem that we threw the baseball in the airplane, to get the resultant velocity, which is what we're really looking for here, the result of the contributing factors, we have to add the vectors together. The sum of the vectors in that problem was just 800 plus 100 is 900. 800 plus negative 100 is 700. The sum of these vectors, 200 plus 50, is the resultant vector. And we can find this, right? We've done this a ton of times. We've done way more complicated questions than this. R, the resultant velocity, which is what we're looking for here, is the square root of 200 squared plus 50 squared. We get 42,000. Sorry, forgot to square root that. We get 207, or 2.1 times 10 to the 2. 2 digits because of the 50. So we end up going a little bit faster as a result of the wind. The wind kind of helps us along there. Problem is, when we want to find the direction, and remember the angle is always measured at the start of your vector diagram, you want to find the direction, it's going to be the inverse tan function of opposite over adjacent. So we end up going a little bit faster as a result of this, but the problem is we end up going off course at an angle of 14 degrees. 14 degrees east of north. So we end up not in Edmonton, but rather we end up somewhere east of Edmonton. Make sense, Taylor? Yes, it should be kilometers per hour. Thank you. Habits, right? There's no reason why we can't stick with kilometers per hour here, because we're not doing an acceleration calculation or something, right? If you want to convert to meters per second, that's fine, but we don't need to. Thank you. Let's do one more example here now. Okay, let's have a look at this one now. It says the captain of a ship aims her ship east at 20 kilometers per hour, but there's a river current putting the ship off course. That river current, by the way, should have been to the north. So 10 kilometers per hour to the north. Where does the ship actually end up going? All right, the first thing that we got to do here is identify solid and dotted line vectors. In other words, things that contribute to where we go and things that are where we go, the result of all the contributing factors. If the captain of a ship aims her ship directly to the east, does that contribute to where we go, or is that where we end up going? What do you say? Yep. Rosie? Yeah, it's contributing to where we're going. So we're going to draw that 20 kilometers per hour to the east as a solid line vector. There's a current of 10 kilometers per hour to the north. A river current. You don't go in the direction of the river current, right? I mean, it contributes to where you go, but you don't end up going there. That's going to be a solid line vector as well. Now, remember, we got to draw this front to back, so we could draw it like this. Or we could draw like this. Doesn't really matter. Okay, I'm drawing it the first way, but it's either way is good. The resultant vector is going to go from start to finish, and that resultant vector is going to be r, and we're going to find the angle there as well, because where we end up going is a vector. R is equal to the square root of 10 squared plus 20 squared, and theta is equal to the inverse tan function of opposite over adjacent, 10 over 20. This time, this side of the room, Nick's side of the room, and over is going to find theta. Everybody over here is going to find theta. And Fraser's side over, everybody over here is going to find r this time. Somebody give me the value of r over here. Taylor, you got it? 22. Okay, 22 kilometers per hour. And that's the right number of significant figures. That's good. And somebody over here have theta? Emma? 27 degrees, what of what? Anyone? North of east, good. We're measuring it from the east axis, so it's going to be north from the east or north of east. Good. Good.